This video describes the circuit used in radar sets for a constant false alarm rate. A false alarm in radar signal processing occurs when a decision is made to declare a fixed target or interference as a moving target. This results in a false target being displayed that does not actually exist. The average time interval between the false alarms is called the false alarm time. The false alarm rate can be calculated for a given false alarm time. The false alarm rate is the ratio of the number of false alarms to a constant reference value, which is usually related to a radar's pulse period. It's important for a radar to keep the false alarm rate as low as possible. A high false alarm rate increases the risk that an alarm will no longer be considered highly relevant. The false alarm rate can be converted into an inverse false alarm rate by taking the inverse. In statistics, however, the concept of a probability of a false alarm is preferred, which can be calculated from the false alarm rate. It is the probability that a false alarm will occur at least once within a given distance, that is, within a range cell. The constant false alarm rate over the entire receiving time is achieved by a special circuit that generates a dynamic threshold value depending on the temporal environment of the target pulse. This circuit is the main topic of this video. This can also be converted into a probability, but it is rarely done. Noise signals are distributed statistically and have amplitudes similar to those of desired signals, which can lead to the appearance of false targets. The false alarm rate refers to the average number of false targets detected at the receiver output within a specific period, such as per antenna rotation or even within one pulse repetition period. The maximum number of potential target acquisitions also determines the maximum number of false targets. This concerns the theoretical case in which there is a target sign in each range resolution cell. In digital radar, this is the number of range resolution cells. In classic analog radar, the maximum possible targets are determined by the ratio of receiving time to transmitted pulse duration. Alternatively, the ratio of maximum range to range resolution cell size could be used. The oscillogram shown contains 6 real targets superimposed by a strong noise level. Only signals that exceed the respective threshold are displayed on a display unit. In this example, the threshold is set high, so that only 4 of the 6 objectives are displayed. This results in a low probability of detection of 66%. If, however, the threshold is set too low, all 6 targets will be displayed correctly, but they would be difficult to see at close range due to the large number of disturbances and noise. All these disturbances are then false alarms. In this image, this would result in a false alarm rate of about 25%. However, in radar, a significantly lower false alarm rate would be desired, with accepted values around 10 to the power of -6. An optimal threshold is somewhere in between. However, even at this point, the probability of detecting a target is only 5 out of 6, or about 80%, and minor disturbances still occur at close range. If the thresholds are represented by a constant DC voltage, the probability of a false alarm is much higher at close range than at a greater distance. Simultaneously, the probability of detection at a larger distance is much lower due to the threshold being set too high. In this example, threshold A would be more favorable in the left half of the oscillogram, while threshold C, in the right half. Therefore, it should be possible to adjust the threshold in areas with strong and weak interference. One way to solve the problem is to create circuits that can adjust the threshold based on the surrounding environmental conditions. This ensures a constant false alarm rate, abbreviated to CFAR, over the whole receiving time. By reducing false alarms, particularly at close range, the probability of detecting targets at longer range is improved, effectively increasing the radar set's maximum range statistically. The simplest approach involves averaging the amplitudes of neighboring cells around each range cell, referred to as the range cell under test, RUT, and using this average to calculate a dynamic threshold, referred to as Z. This circuit is known as cell averaging CFAR. The equation for forming the average involves adding all the voltage values together and then dividing by the number of values, n. Analog radar signal processing requires real delay lines, while in digital radar signal processing, these are essentially neighboring memory addresses for storing the echo signal amplitudes. The blue curve in the diagram represents the threshold value produced by the CFAR circuit. The two high peaks to the left and right of the main target impulse are caused by the inclusion of the strong target impulse in the averaging of neighboring cells, while it is not included in the averaging of the area surrounding the own cell. The main issue with this simple calculation method is that it also suppresses a weak target located close to a strong target. Instead of the simple calculation of the average used so far, a better arithmetic function must be found. In cell averaging greatest of CFAR, abbreviated to CAGO-CFAR, the arithmetic logic is divided into a branch before the cell to be tested and one after it. An average value is calculated in both processing paths. Only the larger of the two values passes into further processing. The advantages of CAGO-CFAR are the low computing power required and the relatively low target losses. Compared to a simple average, the suppression of non-homogeneous interference signal environments is improved. Disadvantages are the still low effectiveness and the possibility that two adjacent target signals can mask each other. The cell averaging smallest of CFAR, abbreviated to CASO-CFAR, uses the same circuit as the CAGO-CFAR. The only difference is that instead of using the larger of the two output signals from the delay lines, the smaller one is used. The larger level of the neighboring target sign is thus usually not used for the threshold calculation. This somewhat reduces the risk of two neighboring target signs masking each other but does not eliminate it, as the illustration shows. The difference between CAGO and CASO is evident on the display, particularly at the edges of larger areas with fixed targets. This is noticeable when there are significant disturbances to the left of the target but not to the right. In the case of the ordered statistic, OS, in the first step, all values of the tapped delay line are sorted in size. A certain number of the highest values are excluded from further processing. An average can be formed again from the remaining values. CAOS-CFAR, or other weightings can be carried out, e.g., depending on the average noise level. Here, too, a separate separation into preceding and following cells can be carried out. Their results can be selected again as greatest of OS-CFAR or smallest of OS-CFAR before further processing. The advantage of OS-CFAR is the significantly improved effectiveness of threshold value creation. Neighboring target signs can no longer mask each other. However, a significant disadvantage is the immense computational effort that has to be provided during real-time processing of the radar signals, since the threshold calculation comes before the target detection. Here, the duration of the calculation would not be so crucial if it were constant for each range cell. But sorting has a different computing time depending on the sequence of the data. This results in different processing times for neighboring cells, which is not allowed for real-time processing. The so-called CASH-CFAR, from cell averaging statistic Hoffel, is also a statistical method developed by Franz Xaver Hoffel, an employee of the former DASA company, now Hensoldt. It is based on a series of summation elements and a special maximum-minimum detector. This method achieves the same advantages as the OS-CFAR. Two neighboring target signs can no longer mask each other. Their temporal side lobes from the pulse compression are reliably suppressed by the threshold. With this method, the time-critical sorting can be dispensed with, so that the computational effort is significantly reduced. However, due to the geometric expansion of the reflecting object, an echo signal is often larger than this one range cell under test. In this case, the edges of the echo signal would be deformed by the circuit. This can improve the contrast, but it would also mean a loss of information. Therefore, the immediately neighboring cells are often not used to calculate the threshold. These cells are then called guard cells. This precaution is not necessary for statistical methods such as OS-CFAR or CASH-CFAR. The circuit we've looked at so far was a simplified version meant to explain its function. In general, the output of a comparator can't be directly used for further signal processing because it would result in all targets having the same amplitude. Instead, this signal can only be used as a control signal for a pin diode switch. In radar, the if amplifier typically has a logarithmic amplification curve. This has the advantage that weak echo signals are better amplified, and strong echo signals are not clipped. However, for the CFAR circuit, a linear curve without separate amplitude and phase processing is preferred. The statistical method used to calculate the threshold values is often the subject of scientific work and military research. This has resulted in the development of various methods, for example, trimmed mean CFAR, abbreviated to TM-CFAR, which is a modification of the OS-CFAR. In digital radar signal processing, several CFAR routines can be carried out in parallel, and a selection function only forwards the result with the best signal to interference and noise ratio, SINR. I hope you enjoyed the video. Thank you for your attention.